Hello students, my name is Rajiv Jha and this is my fifth video on Q&A, question and answer on electrical machine. And in this video you have learned about difference between salient and cylindrical type synchronous machine. So I hope you will like this video and let's begin. So we start with comparison between salient pole type and cylindrical type alternator. Okay, so this is the difference between salient pole type synchronous machine and cylindrical pole type synchronous machine. Okay, so first difference is non-uniform flux distribution, and for the salient pole type synchronous machine, cylindrical pole type synchronous machine, it is a uniform flux distribution actually. And second difference is more stable. Salient pole type synchronous machine is more stable as compared to the cylindrical pole type synchronous machine. Third difference is in salient pole type synchronous machine, there is a concentrated winding on field side actually. Yeah, or we can say on field winding we have a concentrated winding. Okay, so in cylindrical pole type synchronous machine there is a distributed winding on rotor. Fourth one is the difference of low speed machine. Actually, salient pole type used generally for the hydro power plant station or any power plant where low speed where the low speed requirement actually. And for the turbo generator we can use the cylindrical pole type uh, synchronous machine, because at there we have used high speed machine actually. So the fifth one is double axis symmetricity. Okay, so salient pole type synchronous machine we have a double axis symmetricity. That means we used two axes in this synchronous machine, that is called the D and Q axis. Okay, then fifth one is single axis symmetricity. So here we only use the D axis actually, no need in cylindrical pole synchronous machine because of the uniform air gap. So we will all discuss it in detail actually. So sixth one is damper winding are present in salient pole type synchronous machine. There is a damper winding are present to damp out the hunting and negative phase sequence actually. And in cylindrical type pole type synchronous machine there is no need of damper winding. Okay, so we will discuss it in my next you can say upcoming slides. We will all discuss this in detail. Okay, the seventh one is poor EMF waveform and the for the salient pole type synchronous machine, and for cylindrical pole type synchronous machine there is a good EMF waveform. So these type of differences we have counted it seven actually. These seven differences we will discuss in full detail, okay, in my upcoming slides. So let's discuss the first one. So the first one is non-uniform flux distribution and uniform flux distribution. Why it is so? So actually this is all about the air gap. So here we see in cylindrical rotor the air gap is uniform. You will see here the same air gap here, here and here. There is nothing you can say change actually. You will get a same air gap. And here you see the air gap is less. In the quarter form air gap is large, and then less, then large, then less, then large. That means it is a pattern of something, you can say in some place, or you can say that this place is called the pole shoe actually. Okay, so here you see the under beneath of pole shoe the reluctance is very small, and in quarter of this, okay, this the reactance is large. Okay, due to this, because we know phi equal to mmf upon reluctance. Okay, so if reluctance is small then flux is high. So and mmf is if we consider mmf or the armature current is constant over here for a constant load, so reluctance is small, the flux is high. So here the flux is high, okay, and here at this quarter side the flux is low. So in this way we can say the flux is not a uniform, that means it is non-uniform flux distribution in salient pole. Okay, here you see the flux is almost constant because the reluctance is constant. So for the constant flux, phi equal to mmf upon reluctance, you see here reluctance is constant. For the constant load, mmf is also constant, so the flux is also constant. Okay, so due to this we can say here it is a uniform flux distribution. Okay, so this is the differences you understand well. Okay, because of uniform non-uniform air gap, due to this it can happen. Okay, the second one is salient pole is more stable as compared to the cylindrical pole. Why it is so? Because in a previous slide you see there is a large air gap, or on average the air gap, okay, on average here you see the air gap is large. So on average the air gap of salient pole is higher actually. Air gap is higher here as compared to cylindrical rotor. So that is why the here the air gap is high. So air gap is high, that means reluctance is high. Okay, so reluctance is high, that means armature flux. So we can say air gap is high, reluctance is high. Reluctance is high, that means armature flux is low. Why it is so? Phi equal to mmf upon reluctance. So if reluctance is high, so the flux is armature flux is low. Okay, so that is why armature flux is low here if reluctance is high and air gap is high. So then after we can say armature reaction is also, just because of armature, okay, we just tell you what is it. It is directly proportional to air gap, directly proportional to reluctance, reluctance inversely proportional to armature flux, and armature flux is directly proportional to armature reaction. That means armature flux is decreases, so armature reaction is also decreases. So armature reaction decreases, that means armature reaction reactance is also decreases because it is directly proportional to armature reaction reactance. Okay, so armature reaction reactance it decreases, that means synchronizing power coefficient. Okay, synchronizing power coefficient, because synchronizing power coefficient PSY is inversely proportional to the 1 upon XAR or 1 upon XS. Okay, so it is inversely proportional to this. So that is why here synchronizing power coefficient, so armature reaction decreases, synchronizing power coefficient is increases, and we know synchronizing power coefficient is directly proportional to stability. So stability is also increases. So here we see through air gap, if air gap is increases, the stability is increases. In my very first video I will clear all these things, why synchronizing power coefficient is depends on stability. When you just search out my first video, very first video, the size of alternator, we will discuss over there why the size of alternator is for the same power rating, why the size of alternator is larger as compared to induction and DC. At there we will discuss in deep about the why the synchronizing power coefficient is directly proportional to stability, why armature reaction is inversely proportional to the synchronizing power coefficient. Okay, we will discuss it. We actually already discussed. So if you want to deep analysis, then you should first go to the my first video. Okay, so here you just understand when air gap is high, so stability is also increases, so stability is also high. So that's why the salient pole type synchronous machine is more stable as compared to cylindrical pole type synchronous machine. Okay, the next one, this is the actually this is the power for the we talk about the synchronous machine, how the synchronous salient pole type synchronous machine actually, this is the power equation. Here you see there is a two equation, electromagnetic power, and this is the reluctance power. So due to this we will get a higher power stability, actually power stability limit, that's why it is more stable. So through this you can also explain the previous things. Okay, why it is more stable, because it is a within a, you can say, almost del equal to between of 70 to 80 degree, the value of del, you will get the maximum power. So that's why the steady state limit is getting lower with the dial. Actually the load angle with low load angle as compared to uh, cylindrical pole type synchronous machine, where dial equal to 90 degree, with 90 degree we will get the maximum power. Okay, here you only here the angle is in between of 70 to 80 degree, you will get the maximum power, and the maximum power is greater than the cylindrical pole type synchronous machine. That means their limit is also increased in case of the salient pole synchronous machine. Okay, so that's why this is the theoretical way of graph, or you can say that through pedal diagram we can also explain how the cylindrical pole type synchronous machine less stable. Through this you can also judge, actually del equal to 90 degree, you will get the maximum power. Okay, and in salient pole you will get the del equal to 70 to 80 degree, you will get the maximum power. So through this you can say it is get the, and again we can say the maximum power is higher in case of the salient pole type synchronous machine. So we can say the steady state limit is higher in salient pole type synchronous machine as compared to cylindrical pole type synchronous. That is why it is more stable actually. So in this way you can also understand this point. Okay, the third one is concentrated winding. So concentrated winding, because here you see this is the concentrated winding. So that means the all the phase is actually uses the same slots or same part of the pole. So pole actually, so that is why it is a concentrated winding on rotor. Okay, and cylindrical pole we will use the distributed winding. Role of distributed winding, so if we use the distributed winding, there is a some drawback and some benefits we have. So that is the another thing, and another topic actually we will not discuss here actually. We just want to know what is the difference between salient pole and synchronous cylindrical pole. So salient pole and cylindrical pole, the difference is in salient pole we will use concentrated winding, in cylindrical pole we will use distributed winding. Okay, so the next one is, so here this is the 4 point salient pole type synchronous machine, and four point is low speed machine. And for salient pole type synchronous it is a low speed machine, and for cylindrical pole type synchronous machine it is a high speed machine. So for large diameter, actually we here we discuss the salient pole only. For its salient pole type synchronous machine, physically we see it is a large it has a large diameter and low axial length actually. So through the large diameter, if we have a large diameter, so we have to possibility to the pole should be large, or number of poles should be large actually. So the number of poles should be large. So if we know the formula, n equal to 120 F upon P. Through this, if P is the number of poles or large number of poles, that means P is high, then we can say the speed is low. So that is why it is used for the low speed. The simple thing actually. Okay, you have know already. So this is the thing we will discuss here. Okay, so first thing is uh, fifth thing actually, salient. The difference is salient pole is double axis symmetricity. What is double axis symmetricity and what is single axis symmetricity? Actually, in single axis symmetricity, you will use a single synchronous reactance. That means air gap is almost constant in every point between of air gap between of stator and rotor. So it is almost constant. That's why we use a single synchronous reactance over there, okay, to justify the voltage drop. So this is the thing we use it. Then in a second thing, doubly excited symmetricity. So in doubly excited symmetricity, we have to justify the voltage drop with a two, not even one, with a two synchronous reactance. So here we use the two axes actually. One is field in a field mmf, we called is with the field mmf actually. Okay, with the field mmf, this one is called the xt or d axis, and in their quarter form it is called the q axis. So this one is called the two axis phenomena. So that's why it is, because of it uses two axes to justify their reactance. That's why it is called the double axis symmetricity. Okay, so salient pole is a double axis symmetricity, and single axis symmetricity have contained the or have occupied in cylindrical pole synchronous machine. Okay, so the next one is damper winding are present. Okay, what is the role of damper winding actually? So we know damper winding, role of damper winding to eliminate hunting, to suppress negative sequence field. So what is hunting? So hunting is whenever we you can say, if you talk about the salient pole. Okay, sorry. If you talk about the salient pole type synchronous machine, damper winding are present. Okay, in cylindrical pole type synchronous machine, there is no damper winding. So salient pole part, there is a damper winding present because to eliminate the hunting and suppress the negative sequence field. So what is hunting? First thing we will have to in mind. So what is hunting actually? What is hunting? So hunting is nothing actually. Whenever the sudden load change in load is applied, okay, in alternator or a motor, anything happen, okay, in both cases the hunting is possible. So in we talk about alternator. So we take all the concept with respect to alternator. So we talk about this. So if we suddenly change the load, okay, in that case the load angle is suddenly changed, but due to, okay, between of load angle is between of two mmf, no, rotor mmf and stator mmf, there is a load angle. So this load angle suddenly change from you del 1 to del 2 or something, it change actually. So this load angle is suddenly change, but it is not that whatever the new load angle obtained, but it is not stop over there. Okay, because of inertia, because of stator size, because of its rotating, or you can say the saliency, or its salient structure. So the inertia, because of inertia, the load angle is not constant or is not fixed over there, the new load angle. So in that case there is a oscillation between of new and the old. So there is a oscillation between new position and the previous position. So in that case we see it gain a new position after oscillation. So this oscillation sometime you can say it crosses their synchronism. Okay, it crosses their synchronism level, or it crosses their synchronism limit. So in that case, there the instability occurred. So this function, or this from this way we can explain the hunting actually. So because of inertia. So but in cylindrical pole type synchronous machine, the inertia is controlled. There is no inertia type of function over there. Okay, so that's why in cylindrical pole type synchronous machine there is no need of damper winding. Second thing is suppress of negative sequence field. So negative sequence field, whenever you can say uh, whenever the fault is occurred, so there is a three types of thing. First is rotating magnetic field is positive. Okay, actually there is a when we calculate the fault, we break the current into three part. First is positive sequence, okay, RYB. Second one is negative sequence. Third one is zero sequence. In zero sequence there is no rotating magnetic field. In negative sequence there is a negative rotating magnetic field. In positive sequence there is a positive rotating magnetic field. So we want positive rotating magnetic field, we don't want negative rotating magnetic field. So due to use of damper winding, we eliminate the, or we suppress the negative rotating magnetic field. That is the work of damping actually, damper winding. Okay, so first is to damp out the oscillation as soon as possible due to not reaching the hunting position. Okay, the second one is to suppress the negative sequence field. So these two are mostly found in salient pole type synchronous machine, not in a cylindrical pole type synchronous machine. That's why there is no need of damper winding in cylindrical pole type synchronous machine. Okay, hope you understand this. Then at the last, poor EMF waveform and good EMF waveform. So we can say in salient pole type synchronous machine, there is a saliency because of air gap is non-uniform, and there is a torque. You can say reluctance torque is over there. So that's why the EMF waveform is not a you can say uh, is not a good form actually. So it is made it is made with a you can say it is made with a flat top type structure, just like this. That means it is made with harmonics. Okay, so it is not a pure sinusoidal. If you want to have pure sinusoidal, you will have to put some extra effort in the designing part. Okay, so in salient pole type synchronous machine, we will have a poor EMF waveform. That means it is a uh, because of pole shoe. Okay, because of pole shoe, it has a flat top type of AC actually, or sinusoidal waveform we will get. Because of this, it is have a poor EMF waveform. And in cylindrical, we have a good EMF waveform. As we know, we will get a pure sinusoidal waveform over there. Okay, so these type of differences between of salient pole type and cylindrical type of alternator we have. Hope you will like this video, and I think you have make a good concept what is actually the difference between a salient pole type synchronous machine and cylindrical pole type synchronous machine. Hope you like this video. Thank you very much.